This is the solution video for problem set 7, problem 3, and this question asks us to start off with a solution strategy. And so essentially what I'm looking at here is a 4-bit register that receives user-defined inputs K1 and K0. And I'm going to pull out the problem definition just to point at it for a little bit. And we notice that, well, one, they're all exclusive, and basically we're going to be picking between these different functionalities of the register based upon these inputs. So if we're picking between different inputs, then basically we just want a multiplexer. And since I have 2 bits that I'm using to select, I'm going to have a 4-to-1 mux in front of each flip-flop. And the next important thing is basically, since I'm designing a register that does shifts primarily and parallel loads, these 3 functionalities are much easier to do with a D flip-flop, and so I'm going to make the primary part of my register out of D. Well, sorry, that's not correct. I will make my register out of D flip-flops and basically use the logic here. This binary up counter will be a little bit of a pain in the rear to do because Ds aren't really designed to do counting. But we can design the logic for that as well. And so basically I'm going to have to, basically use next state tables to determine how my counter is going to count up, and then use K-maps to minimize that, and then basically draw that circuit and put that into the 0-0 input of my multiplexer. And then my arithmetic right shift, I'm going to have to make sure that my most significant bit gets fed into itself, but then the rest of them get fed down. For the circular left shift register, I'm going to need to make sure that basically my least significant goes up, and that one goes up, and then the most significant bit gets cycled back down to the least significant bit. And then for the parallel load, I'm just going to need to have 4 parallel load bits, and I'm going to need to put those into the 1-1 selection. And so that's how I'm going to solve this problem. And let's get going then. So as I said, I'm going to want to use D flip-flops as well as a mux in front of each input. Actually, I'm going to make this my mux. So this is a 4-to-1 mux with inputs 0, 1, 2, 3, and S1, S0. And I'm going to want a D flip-flop here. And keep these small so I can actually fit everything on the page, hopefully. D, Q, Q bar. And this is also going to have a mux. 0, 1, 2, 3, S1, S0, 4-to-1 mux. And 0, 1, 2, 3, S1, S0, 4-to-1 mux, D, Q, Q bar, and one last one, S1, S0, 0, 1, 2, 3, 4-to-1 mux. And since I foresee a lot of wires being drawn, I'm just going to define my signals here, that this is going to be Q3, Q2, Q1, Q0, and rather than draw wires up to these muxes, I'm just going to write the Qs up there. And this output goes into here, this output goes into there. And then I'm going to need a clock signal to make sure that these all load synchronously. And what else am I going to do? So I'm going to start off with the easy ones, the shifts in the parallel load. So the parallel load needs to be when K1 and K0 are both 1. And so I'm going to have parallel load bit P3, parallel load bit P2, P1, P0. And then for K1, K0 is 1, 0. The register should behave as a circular left shift. So left shift, Q0 is going to go here, Q1 is going to go here, Q2 is going to go here, And Q3 is going to cycle around and go there, just like I said in my solution strategy. Arithmetic right shift, Q3 is going to go back into itself and get shifted down. So we were sign extending. Q2 is going to shift right, Q1 is going to shift right, and we're not going to put Q0 anywhere. That bit is just going to get lost.